In this lesson, we're going to look at how to divide radical expressions. This first video that we do will concentrate on radicals that have monomial denominators. That means a single radical in the denominator. So there's a property here that we're going to use kind of as our underlying principle that says this, which sometimes when students look at these math symbols, it doesn't mean a whole lot to them. All this is saying is that if you have some radical divided by some other radical, and they are the same index, you can write them as a quotient underneath one radical symbol. So what does that mean? Well, all that's saying is that if you had the square root of 10 and you wanted to divide by the square root of 5, that's the same thing as the square root of 10 divided by 5, which would be the square root of 2. Now, the indexes have to be the same, so you couldn't divide a square root by a cube root. That wouldn't work. But if these are the same, you can make one large radical symbol, and then below that radical symbol, just put your quotient. So in this case, 10 over 5. And then you divide those like regular numbers. 10 divided by 5, answer would be radical 2. That's all that means. If I had the fifth root of 15 divided by the fifth root of 3, they're both fifth roots. They are, one will divide by the other, so you can write it as the fifth root of 15 divided by 3. 15 goes evenly by 3. That is the fifth root of 5. And usually once we get going, we'll start skipping this middle step right here, where we'll just say the fifth root divided by another fifth root. Your answer will just be the fifth root of whatever you get when you divide those two. But it's really important. It's like multiplying. You can only, in multiplication, multiply a radical by another radical. Well, dividing, you can only divide radicals by other radicals. So for example, if I said, what's the square root of 10 divided by just a regular 2? Students are often tempted to say, oh, that's the square root of 5. No, it's not, because you've got a square root divided by a non-radical. You cannot do that. This would not simplify. It would equal exactly what it is right now, because they're not radicals, versus if it had been the square root of 10 divided by the square root of 2, now I can divide them because they're both square root or index 2 radicals, so I can divide them. My answer will just be this radical divided by this, and the answer is also a radical. When you divide that radical by this radical, your answer turns out to be a radical. All right, so let's put that into play, that property, and see if we can work our way through some of these examples. Now, unfortunately, that starts out fairly nicely. They're not always going to work out that nicely, but that's going to be our underlying principle that gets us started in through these. Okay, so we'll start with the first one. I think we'll have not too much trouble here in the beginning. The square root of 15 divided by the square root of 3. They're both square roots. They do divide evenly. That will very easily work out then to be the square root of 5. Now, we progress a little bit, and this time I have coefficients. Well, these are just regular numbers. As long as there's no addition or subtraction or anything mixed in here, that makes this all one term up here, and this is all one term down here. So I can just divide them, but it's like multiplying. You multiply the coefficients by coefficients and the radicals by the radicals. The same holds true for dividing. You divide coefficients, so 24 divided by 3, that would be 8. The square root of 48 divided by the square root of 12. 48 divides by 12 4 times. Now, you would never leave your answer like this. At this point, radicals become like fraction work since middle school. You would never leave fractions not in simplest form. You would never leave radicals not in simplest form. 4 is a perfect square, so I would never leave that like it is. I would just say, well, the square root of 4 is just 2. 8 times 2, 16. Now, sometimes what will happen is student A will do what I just showed you. Student B will say, oh my goodness, I didn't do it that way. I did it in a different way. It took me a lot more work, but I got the same answer, which is fine. As long as you're using properties that are mathematically correct, then you're going to end up at the right answer in the end. Sometimes students will look at this and they'll kind of remember, oh, I remember that we can always simplify the radicals. Maybe in the beginning, if we simplify first, that'll be easier. Now, with multiplying, that was true for sure, because if you're going to multiply them, the smaller the radicals are, the smaller your answer is going to be when you multiply them. But here, when you divide these, you could do this instead. So 24. Simplify that radical. 48 is 16 times 3. So the square root of 16 is 4. Radical 3. 12 also simplifies. The square root of 12 is, 12 is 4 times 3, and the square root of 4 is 2. Radical 3 left underneath there. So now I've got 24 times 4, which is 96, square root 3. 3 times 2 is 6, square root 3. Well, 96 divided by 6 is 16. The square root of 3 divided by the square root of 3, anything divided by itself, always just gives you a 1. 16 times 1, 16. Same answer, different method. In both cases, I was applying properties of radicals that were correct, which will ultimately lead you to the correct answer at the end. So don't worry if you're not doing it the exact same way that I do it when you do a solution or your neighbor's doing it. As long as you're doing things that are mathematically correct, you will be fine. Okay. Let's look at these two we have here. Now out front this time, 7 over 14 doesn't divide evenly because the numerator is smaller than the denominator. However, the fraction 7 over 14 does reduce. We just reduce it like you would fraction. 7 over 14, that's 1/2. Now you divide these because they're both cube roots. We're allowed to divide them. 320 divided by 10 would be 32. So this one will be cube root 32. Again, great start. However, radicals now are like fractions. We must always check our final answers and make sure they are reduced or simplified as far as possible. Cube root. You should say, well, are there any perfect cubes that divide into 32? Well, really, you only have two options. 8, which does go into 32. The only other perfect cube that's even smaller than 32 is 27. Therefore, we're going to use cube root of 8 times 4. That's how I will get 32. The cube root of 8 is 2. So I'm going to have 1/2. Now I'm going to simplify this radical. So it's 2 cube root, what I said is 8 times 4. So there'd be a 4 left underneath there. Well, now I've got a 1/2 multiplied by 2, which means these 2's will just divide each other out. And our final answer for that expression in simplest form would be the cube root of 4. Right, another one to look at here. So we've progressed a little bit. As you can see, we have coefficients. This time the coefficients have variables with them as well. And then we have our radicals. Well, let's look at what we can do here. So let's start with the coefficients. I've got negative 8x to the 5th divided by 3x squared. Let's just completely ignore this stuff for a second. 8 over 3 does not reduce. So there's nothing I can do with those right now. They're going to stay the way they are. X to the 5th divided by x squared, you subtract the exponents. 5 subtract 2, x to the 3. Now these will divide each other out. So square root, they're both square roots, so we're allowed to divide them. 48 divided by 2, 24. Now the exponents, when you divide, you subtract them. So 11 minus 3, x to the 8. This radical is not in simplest form. We're going to have to continue. Again, this is a great start, but our answer is not reduced. So it would be comparable in middle school, leaving an answer as 6 over 12, when you should know that you should be able to reduce that to 1 over 2. All right, so we're going to go negative 8 thirds x cubed Now this square root. So 24 is divisible by 4. 4 times 6. The square root of 4. Actually, let's put it over here. Let's show. This would be 4 times 6. X to the 8th is already a perfect square because I can take half of it. So that I'm just going to leave it like it is. This is all considered, even though you say, oh, do I put it the line all the way over here? You don't have to. You can. It's part of the numerator or just out beside it. It all means the same thing. I've got negative 8/3 x to the power of 3. Now 4 is a perfect square and x to the 8th is a perfect square. So we're going to take the square root of those. Square root of 4 is 2. The square root of x to the 8th is x to the 4th. So the only thing under there that was not a perfect square is the 6. We're getting there. Now I've got 8/3, negative 8/3, multiplied by 2. So I'm going to multiply the numbers. That'll give me, now remember, the number 2 is assumed to be over 1. So when you multiply fractions, it's just straight across the numerator, straight across the denominators. Negative 16 over 3. When you multiply variables, you add exponents. X to the 7th, and then we've got our square root 6 left underneath there. Their final answer. So you can see that one kind of got a little bit more complicated. We had to kind of know our stuff to work our way through that one. Well, these 4 examples, you'll notice that in every one of them, the numerator, the radical in the numerator, divided evenly by the radical in the denominator. Well, what if the world is not so perfect? What if that radical in the denominator is not going to divide evenly into this? Then what are we going to do? Well, what we're going to do is we're going to learn a new process that we call rationalizing the denominator. This becomes an important skill moving forward in pre-calculus. We are not allowed to have radicals remaining in the denominators of our answers. And this process, if I'll just scroll down so you can see here, to rationalize means to convert to a rational number without changing the value of the expression. So my answer is going to be equal to this. If I was to take a calculator and divide this out, and then take my answer and divide it out, which I'll do at the end just to prove it to you, they're worth or equal to the exact same thing. Here's the difference. The radical in the denominator, we're going to get rid of it. And the way we do it is by multiplying the numerator and denominator by whatever square root or radical that you see in the denominator here. Now that may sound confusing, so hopefully I can clear it up for you here with an example. So if I looked at this, for example, and I say, well, these won't go evenly. Not as nice as the last 4 examples. So what we're going to do is we're going to multiply this expression by a fraction that we would consider to be equal to 1. You say, well, how do I know what fraction to pick? It's all dependent upon the radical in the denominator. So in the denominator, I see a radical 6. I am going to multiply the numerator by radical 6 over radical 6. Now sometimes students say, well, you can't, why? Oh, what are you doing? You can't do that. Yeah, I can do that because anything divided by itself, this big bracket here is nothing more than a big number 1. Well, if you were to take some fraction and multiply it by the number 1, does it really change the value of anything? No, because anything multiplied by the number 1 is just that number. But here's what it does. Our goal is to get rid of, we don't want radical signs in the denominators of answers. When I multiply the numerator, square root 10 times square root 6, that's the square root of 60. Now watch what happens in the denominator. Because these radicals are the same, the square root of 6 times the square root of 6, I'll show you here the first one. The square root of 6 multiplied by the square root of 6 is the square root of 36. And we've talked about this back when we did multiplication. And the square root of 36 is just a 6. If you have the square root of a number and you multiply it by the square root of the same number, you should know without even hesitating, it's just that number without the radical. So for example, if we had the square root of 11 and I multiply it by the square root of 11, I don't have to multiply that all out. I know the answer is 11. If I have the square root of a happy face and I multiply it by the square root of a happy face, I just get a happy face. So when I go down here and say, well, I'm going to multiply the square root of 6 by the square root of 6, I don't got to even hesitate. I know the answer is 6. Now be careful. Don't then soon say, oh, now I can divide these and say that it's radical 10. No, you cannot, because that's a square root. That's not a square root. But what you can do is simplify this radical. 60 is divisible by 4, so you could change that into 4 multiplied by 15. The square root of 4 is 2, radical 15. Divide that, or sorry, leave that as a 6 for now. Now your coefficients, you've got 2 over 6 out in front. Well, that fraction 2 over 6 can be reduced to 1 over 3. Now, I don't really need the 1 there, so I can just put radical 15 over 3. And again, you understand hopefully that there's a 1/3 there because all I've done is reduce the fraction above 2/6 to 1/3. And again, you do not need to put the 1 there if you don't want to, just put it there for visual effects so you can see how the 2/6 became 1/3. And that's what we do. That is called rationalizing the denominator. Now I'm going to prove to you. So that is called rationalizing the denominator. Now, if you stick around denominator, your pre-calculus courses, by the time you hit grade 12, well, actually, in some cases, just because of the process we're getting into, we actually may rationalize the numerator. But for this course, we're only going to ever rationalize the denominator. Now, I'm going to take my calculator and get the value of the original expression, the square root of 10 divided by the square root of 6. And then I'm going to take my answer, the square root of 15, and divide it by 3 and prove to you that these are actually equal. All right, so okay, so I just calculated that first one, the original question. When I put that in the calculator, I got 1.29. Oh, and there was some other stuff there. Now I'm going to check this and see if this, after all that stuff, is really still equal to the original. I'm going to take 15 square root, and I'm going to divide by 3. And guess what? Same thing, 1.29. Oh, and again, we should not be surprised at that because what's in red here was nothing more than a number 1. So multiplying anything by the number 1, although it changed what it looked like, it shouldn't change the value of it. So that's how rationalizing the denominator works. Let's try a couple of those. Okay. Well, I look here. Right away, these don't divide because that's a non-radical and that's a radical. So I'm going to rationalize the denominator. So to do that, I'm going to multiply by square root of 12 over the square root of 12. Whatever radical's in the denominator, you multiply both the numerator and denominator by that same expression. Now I've got 6 radical 12. The bottom becomes 12 because it's square root of a number by the square root of that same number. You just get the number without your radical. 6 over 12 is going to reduce to a half. Or you can, let's hold off on that for a second. Let's leave the 6 here. Let's simplify this radical. 12 is 4 times 3. The square root of 4 is 2 times the 6. It's going to give me 12 radical 3. And then there's going to be a 12 left down here. 12 divided by 12, just 1. Or, as we like to say, those just kind of canceled each other out. There's your final answer, square root 3. Now, there's no radical left in the denominator because the denominator ended up being just a 1. Now, don't get fooled into this one. Here, radical 28 divided by 8 does not go evenly. So what we're going to do is reduce 28, 4 times 7. So 2 root 7. 8 is 2 root 4 times 2. Square root of 4 is 2 radical 2. Now you'll notice, so how come you're simplifying them first? You really didn't have to. I just did that so that when I went to rationalize, I wouldn't have to multiply such big numbers. It just made them a bit smaller. So sometimes it's to your advantage to reduce in the beginning. Sometimes it's not. You kind of get experience and figure out which way is the best. So those divide each other out to give you a 1. Now I'm down to radical 7 over radical 2. Not allowed to have radicals in the bottom. So I'm going to have to multiply by square root 2 over square root 2. That's how you rationalize. Multiply the two radicals. Radical 14. Radical 2 by radical 2. You just get a 2. Finished. Can't divide those because one's a radical, the other one's not a radical. All right, couple more. I think like the last one, I'm going to reduce first here just to see what happens. Square root of 18. 18 is 9 times 2. Square root of 9 is 3. Times that 12. You're going to get 36 square root 2. 8 is 4 times 2. Square root of 4 is 2. Times that 8. I'm going to give you 16. Ooh, that worked nice because now look what happened. These two radicals are exactly the same. I can divide those out and just give me a 1. Anything divided by itself is 1. All I'm left with is 36 over 16. Now, hopefully you would never leave your answer like that. Those reduce. Everything here will divide by 4. And that will give you the fraction 9 over 4. All right, last one. Oh, we've got some variables now this time. Well, even if there's a coefficient here, that doesn't make any difference. You're still going to multiply by whatever radical's in the bottom, not the coefficient. So in this case, I want to rationalize the denominator. So I'm going to multiply by the square root of 5a cubed over the square root of 5a cubed. So as I said, notice it's just the radical part, not the coefficient. Now, truth be told, you can use the coefficient if you want, because it's still equal to 1, but it just makes for more reducing in the end. So if you want your life to be as easy as possible, just multiply by the radical, not the coefficient. All right, here we go. These are going to multiply, so we've got a negative 3 in front of this one, a 1 in front of this one, so I'm going to get negative 3. Two radicals. I can multiply them together and put the answer below a radical. Answer will be 40 that's 8 times 5. Now add the exponents. That's going to be a to the 4th. A, so it's a coefficient. The coefficient here is a 1, so a times 1 is just a. Anytime you multiply a radical by the exact same radical, the answer is just going to give you 5a cubed. All right, let's see what we've got here. Negative 3. This will reduce. 40 is 4 times 10. A to the 4th is already a perfect square because you can take half of the exponent. In the denominator, when you multiply 5a cubed by a, you're going to get 5a to the 4th. All right, so now, here, let's see what we've got. So 4 is a perfect square, and a to the 4th is a perfect square. 10 is not a perfect square, so it's going to stay underneath the radical. Square root of 4 is 2. Multiply by the negative 3, I get negative 6. Square root, oh, sorry, I forgot one thing. So it's going to equal, let's try that again. Square root of 4 is 2. Multiply by 3, that's negative 6. That was right. But I also have another perfect square here. The square root of a to the 4th is a squared. That's going to come out front, leaving me with a 10 below the radical. Denominator, 5a to the 4th. Now, negative 6 over 5 does not reduce. That fraction is going to stay there. A squared divided by a to the 4th. Well, you got two options here. The rule is you subtract exponents. 2 subtract 4 would be a to the negative 2. However, often we don't like to put negative exponents. So another way to look at it is that you've got a multiplied by a in the numerator, and you've got a multiplied by itself 4 times in the denominator. So I would say, well, how many? Where's there more of them? Well, in the bottom, there's 4 of them. In the top, there's 2 of them. What happens is these 2 will cross out 2 of these, leaving you with a squared in the denominator because there was more of them down there. Or if you don't want to write it that way, you can put a to the negative 2 if you want to write it in the numerator. And then your radical 10 would still be up in the numerator. Now that would be reduced. So as I said, or you could have negative 6/5 a to the negative 2 radical 10. That's the exact same thing. All right, so that's where we're going to end our introduction to division, and we'll give you some practice questions to go with those as well.